Today's multiplier property for an exponential function of the form y equals ab to dx. If the value of the independent variable increases by 1, the value of the dependent variable is multiplied by b. We've sort of seen it before, and there's a proof for it. It's f of k equals ab to the k, where if we add one more, in other words, if you go to the next case scenario, you have ab to the k plus 1. And now as we expand this, notice we separate the base into ab to the k times b to the 1. Notice ab to the k was what we started with, so that's actually our f of k. So on our last line there is f of k plus 1 is just equal to f of k times b. Well, it's kind of hard to visualize it there, agreed? So here's a reference real quick. This is from a previous video that you may have seen already. F of x equals 2 to the x. Once again, note the base is 2. If you plug in the first case scenario of -3 when x is -3, well, you want to simplify that. So you take the reciprocal. And once again, we've already sort of explained through this in the previous video. But for reference, notice that the answer becomes 1/8. Okay, so the next value, if you multiply by 2, 1/8 times 2. What does that give you? Well, let's try it out. Let's check our calculator real quick. 1/8 times 2. 1 divided by 8 times 2. That should give us 1/4, which is 0.25, right? We can go to math, fraction, have it converted. Yeah. And we can go 1/4 times 2. Notice each time we're multiplying by 2, we get 1/2. Math, fraction to convert it, we get a half, just like the answer that we got next. And then if you go 1/2 times 2, you get a 1. 1 times 2, 2. 2 times 2, 4. So this is basically what this is stating. The fact that our base is 2, we can multiply the previous value by the base of 2 and get the next value. That is what the base multiplier property tells us. Well, let's take a look at another property. Increasing or decreasing properties. So for y equal to ab to the x, where a is greater than 0. If b is greater than 1, then the function f is increasing. We say that the function grows exponentially. So we have exponential growth graph on the bottom left. That's what it would typically look like, or something similar. If, on the other hand, the v value is between 0 and 1, or in other words, 0 is less than b, which is less than 1, then the function f is decreasing. We say that the function decays exponentially. So there's a graph of exponential decay. You may have seen previous graphs of this. So here's a quick reference once again. If we have, for instance, one case scenario, let me turn it off, that way you can see the graph. And I'll graph just the first one. This is our exponential growth, first equation. And in this case, it's of 2 to the power of x, first graph. Let's go to y equals again. I'll go ahead and turn this one off by going to the equal sign, hitting enter, pushing down, and the next equal sign, hit an enter to turn it on. Notice it highlights it. There we go. The one that's highlighted is the one that's going to graph. I hit graph, and now I can see the other one, the exponential decay. There we go. It means it's going down from left to right versus going up from left to right. We also have what we call horizontal asymptotes. Horizontal asymptote. From previous examples, it can be noted that as the value of x grows or becomes smaller, the resulting y value becomes closer to 0 but never reaches it. So we have on the left side exponential growth, and on the right side exponential decay with a horizontal asymptote on your x-axis. So I do believe I've showed this previously in previous videos, but let's go ahead and go back for reference. In this case, we have a graph on there. If I try zooming in to the right, it seems like it stopped, but it didn't. It's still graphing ever so closer. So if I try doing a quick zoom box, Z-box, that way we can see it on there. There is my cursor, that way I can see where I'm graphing at. I want to zoom in closer to this area where it looks like it stopped graphing. but it really didn't. I'll hit enter once, push up, and go to the right. That way I can see a box made. And I'll hit enter in this region. Now I can see where my graph looked like it stopped. No, look, it's still going. And even though now it looks like it stopped still, it's still graphing ever so closer to the x-axis. Let's try another zoom back real quick. And I'll do it once again closer and closer to this region. I'll hit enter, push down, go to the right, where it seems to have stopped, and hit enter again so that I can zoom into that region. And look, it's still graphing more and more to the right, except we are not able to see it on the larger scale because it's so tiny. So let me go back to the larger scale, go to zoom and do a zoom standard, option 6, to view my regular size. There it is. And notice it, once again, it never reaches the x-axis. Let me backtrack and turn on my other graph by hitting enter on the first one, first equation sign or equal sign, and I'll graph both of them. There is both my exponential growth and an exponential decay in the same graph, with both of them having a horizontal asymptote. So going on to the next one, notice we also have what we call a reflection property. So reflection property tells us that the graph of f of x equals ab to the x and g of x equals negative ab to the x are reflections across, primary reflections of each other across the x-axis. That just means that if we have a positive a value, they would be our regular graphs. Once again, here's a view of our regular graphs up above the x-axis. They're positive. On the other hand, if I make them negative, then we would have graphs that look like what we have there. Do notice each graph has two different graphs. Just like I have two different graphs on my calculator, but let's put 4 of them. Let me turn one of them off for reference. So I'll turn this one off, and I'll make one similar to the very first graph. I'll make it a reflection by saying it's a negative 2 to the power of x. And that's what's going to make it a reflection. And I will graph both of them. There's my first graph coming up, first graph, and then the reflection of it coming up as well. There it is. There's my reflection. So that way you can see there's really 2 graphs in one there. One has a positive a value, one has a negative a value. Be aware of that. Domain and range. So the domain of any exponential function of the form f of x equals ab to the x is the set of all real numbers. The range of the exponential function of the same form, where a is greater than 0, is the set of all positive numbers. Where a is less than 0 is the set of all negative numbers. So in other words, for the domain of x, we can use any number. So domain is the x value, right? We can use any number, all positive or negative numbers, or 0, which is a neutral number. On the other hand, for the range, the y value, we can use only positive numbers or only negative numbers. So be aware of that. Hence why we say we have a reflection in this case. We can either use positive y values or negative y values. Let me go ahead and turn this off real quick. And this is for our first equation, first graph. You'll notice that it only shows positive y values. That is the range, only positive y values. If I go back and turn that one off and plot the negative side of it, I turn it on, there we go. Now we can see only negative y values. So there is the range. It does not cross our x-axis for this particular case. So domain and range examples.